So next we have Greg Harris with Next Generation Nerve Repair.
Thank you.
Thank you.
All right, so I'm Greg Harris. I'm an assistant professor at Cincinnati in the University of Cincinnati in chemical engineering. And I'm going to talk to you today about our solution for nerve repair. So the team is myself and Dr. Layla Esfandiari, who is an associate professor in biomedical over there at UC. Previous appointments for both of us, I was at Princeton University and a joint appointment at the Mayo Clinic, and Dr. Esfandiari was at UCLA doing research before we both moved to UC. So I'm going to start off with a little story about a car crash that Pat was involved in that led to traumatic injury. So he suffered trauma to the upper body and had severe peripheral nerve damage. This led to a lifetime of issues for Pat because the surgical solution was not good enough. So why didn't Pat's nerves just heal on their own? You can see here my crudely drawn schematic with a nerve bundle innervating some muscle. The muscle's in red, that nerve changed color on this projector actually. It's green up there. So in a nerve injury, you're gonna have a gap there, right? It could be crushed, it could be severed, something could happen to that nerve. It just does not have the physical guidance to bridge that gap. You can think of this kind of like a car driving across a bridge. That bridge isn't there, if that guidance isn't there, that car is gonna go right into the river and float away. That nerve can't grow across there if it doesn't have the guidance. The protein molecules are what makes up that bridge, and if there's no footings, there's not gonna be a bridge there. The electrical messages and every other message telling that nerve to heal, to go across, can't get through in that situation without that bridge. And what happens, which is what happened to Pat, that nerve atrophies, goes away, and then your muscle atrophies, or your skin, or whatever it is that that nerve is innervating. And Blue Cloud gave a nice primer, actually, Ira, talking about how you have that pain down in your heel. Without that nervous system, you can't do things you enjoy, like sports. So what's the current clinical solutions out there? End-to-end connection, where you just pull those two together. That doesn't work in traumatic injury because you can't pull nerves. Nerves don't like pulling on them. Nerve grafts, which is what Pat had happen, where you take nerve, usually from the sural nerve in your heel, and you put that somewhere else. That has a pretty low success rate. Maybe 50% if you're lucky. It did not work for Pat all that well. You have a loss of sensation in your heel, and then the downstream application may not even work. And then what's really coming into focus now in engineering labs, medical labs, are nerve guidance conduits. So you're making that physical structure as a bridge, but these aren't really ready for prime time yet. There's not a lot of clinicians out there that really use these for the traumatic injuries. So to kind of take this broader than Pat, we need clinical solutions for nerve injuries across the spectrum, whether that's sports injuries, cancer surgeries, resection of tumors, battlefield injuries, all across the spectrum. If you don't have that healthy nervous system, so in blue on that human over there, you're seeing all of the peripheral nerves. It's innervating everything, all your tissues, your skin, your muscle. Without that healthy nervous system, you can't do the things you enjoy, and that affects a lot of people out there. So we want to address that overarching problem. Kind of again, just talking about what's happening there. In this nerve conduit, you're going to have that fibrin cable, that green, that's kind of your bridge, right? And when you get those signals, you get that bridge, you put it all together, you are going to have the cells move in and kind of fix that nerve. So that's what we're shooting for there. And you need a lot of things for that to happen. You need all those signals, you need those protein molecules, you need that bridge. So our solution addresses that with the bioactive ECM. So that's kind of the proteins, that message. The piezoelectricity is kind of those electrical signals telling that nerve to grow. Putting that all together with less inflammation, and it can be non-invasively stimulated to grow those cells and that nerve across that bridge to get functional healing. So that's where we are. The market size for this, bioactive materials, so that means those proteins. is about 2.27 billion, expected to more than double by 2028. Digging a little deeper into the peripheral nerve injury market, specifically in that trauma, it's about 1.43 billion, expected to double in the next 8 years as well. So this is a sizable market, and there aren't really any viable clinical solutions for these traumatic injuries out there right now. So where we stand now, we have about $1 million in funding from the University of Cincinnati, the Department of Defense, think injured warfighters there, and the National Science Foundation. We have a patent on this, and we have preliminary animal studies that have actually just begun, starting to look at the integration of this into the system. So what we are asking is an EIR to help facilitate the process from kind of the academic space, basic science, looking at this, into advanced animal models, kind of looking beyond where we are now with our animal models, and then ultimately commercialization. So with that, I just want to thank everyone for coming, all the EIRs, and we've been willing to take any questions.